Hey everyone, welcome back to Math 30-2. Today we're looking at Lesson 3 of the Probability Unit, mutually exclusive and non-mutually exclusive events. Now, the first thing is a definition. Mutually exclusive events. These are two events that cannot occur at the same time, and they are said to be what's known as disjoint, meaning if something is not joined together, it's disjointed. And this really can be seen when we look at the Venn diagram. These two events, event A and B, are considered disjoint or mutually exclusive because none of the elements of A are in B. There's no overlap. So when we look at the probabilities of mutually exclusive events, we see that we have the probability of A or B equals the probability of A plus the probability of B. And we know that the probability of A or B is really just the union of those two. Now, if we're uniting two things that aren't touching each other, then again, the probability is A plus the probability of B. This means that the intersection, or something that is in both A and B, the intersection has to equal the empty set, or in other words, the probability is 0. So now for non-mutually exclusive events, those are those ones that do have an overlap, or in other words, they are events that have some common outcomes. So those are the ones that have something in the intersection area right here. So this event A is not mutually exclusive with B because it shares some common outcomes. And in this case, when we look at the probabilities of these, we want to look at the probability of A or B equaling the probability of A plus the probability of B minus the overlap. Because if there's the probability of A, that's going to count everything inside this circle right here. So if we have that probability there, and then we have the probability of B, which is over here, that means we've counted the probabilities of twice right here in the middle. So that means if we do not subtract one of the intersections, we'll have counted it twice. So that's why here, when we do this, we have the probability of A and or B, equals the probability of A plus the probability of B. Again, minusing the intersection. So we want to minus that one so we don't count it twice. Now, we are going to look at some examples here of events that potentially are mutually exclusive and not mutually exclusive. So in 1A, the experiment is we draw a card from a standard deck. Now remember, we have 52 cards in a standard deck. Event A is we are drawing a face card. Okay, remember the face cards are the king, queen, and the jack. And there are one of those in each suit. And remember, there are 4 suits in a deck of cards. And in that, we have the diamonds, we have the hearts, we have what else? Oh, we have the clubs. Excuse my club. That's what a club looks like. And then we also have the spades. Okay. And the next event B is that a diamond is selected. Okay. So we're wondering, can these two events happen at the same time or not? Can we have a face card that is also a diamond? That's the question we're going to ask ourselves. Well, in this case, yes, we can. For instance, we can have the king of diamonds. And we just have to have one thing where both of them occur at the same time for something to not be mutually exclusive. As long as we can find one, then we know, in this case, they are not mutually exclusive. Let's look at experiment 2. We're throwing 2 dice. The first event of A is the dice shows doubles. And remember what we mean by doubles is mean the same number appears twice. So we could have, for example, 2 2s or 3 3s, something like that. Now, event B is that the total score is 8. So we have to say, can these two things happen at the same time? Well, they sure can, because if we roll a 4 and a 4, this is not only doubles, but 4 plus 4 also equals 8. So again, these are not mutually exclusive. And C, experiment. 2 dice are thrown. Same thing again. This one, event A, is the dice shows doubles again. But in this one, the total score is 9. Well, without having to add all of these up, remember, if we have two numbers that are the same and we add them together, they're always going to be even numbers. For example, if we have a 1 and a 1, that's going to be a 2. So the total equals 2. If we have a 2 and a 2, that equals 4. So we will never get doubles that are an odd number. Therefore, we cannot have doubles that equal 9. So these events are mutually exclusive. I'll start working a little bit with the formula. It says determine whether the events A and B are mutually exclusive. Now remember, for mutually exclusive, that there are no overlap. In other words, there are not events that are both A and B. In other words, the probability of the intersection equals 0. So we want to figure out, do these two events A and B, are they mutually exclusive? Well, the way we're going to do that is we're going to find, is the probability of A union B equal to the probability of A plus the probability of B? Now remember, 4 represents our union. So if we have 2/5 and we have 1/5 for B, that makes 3/5 for the union, which is the OR. Therefore, these two events are mutually exclusive. Let's try another one. Here we have the probability of A of 0.3, the probability of B of 0.4, and the probability of A or B is 0.6. So going back to the formula, probability of A or B, or united, equals the probability of A plus the probability of B. Now, while I know it seems that we're doing example after example, and I'm always writing the formula down, this is something what I want everybody to get into the habit of doing. On a diploma, you're not, the person marking it needs to understand what you know. And so by putting down the formula as the first steps, nobody has to guess your thought process. So make sure we get into that habit. So we're going to put in 0.3 plus 0.4. Now that equals 0.7, and 0.7 does not equal 0.6. So in this case, these are not mutually exclusive events. So they can occur at the same time. In other words, if we looked at the Venn diagrams of these two events, we would see something like this, where there is an overlap here. Okay, so let's look at number 3. Events A and B are not mutually exclusive. So the probability of A is 0.4, the probability of B is 0.3, and the probability of A or B is 0.65. So notice that if we added these two together, 0.4 and 0.3, that's 0.7, which does not equal 0.65. So definitely not mutually exclusive. And they're asking us to find the probability of A and B. In other words, we're trying to find the intersection. And over here, the probability of A or B, we know that is the union. So going back to our formula, we have the probability of A or B equals the probability of A plus the probability of B, and we're going to minus that intersection so we don't double count it. Now let's fill in what we know. We know that this is 0.65, probability of A is 0.4, probability of B is 0.3, and we're going to subtract the probability of A intersect B. Let's simplify. So we get 0.65 equals 0.7 minus the probability of A intersect B. Now I'm going to subtract 0.7 from both sides. And this is going to give me a negative 0.05 on this side and negative probability of A intersect B on this side. Now keep in mind, probability can't be negative. So make sure if you ever end up with a negative, look over here. It's like, oh, okay, I have a negative on both sides. Well, this is really the same as having a negative 1. We can either multiply both sides by negative 1, and that would just cancel those negatives right there, so that the probability of A and B, or the union, equals 0.05. Okay, let's look at number 4. If events A and not B, remember that little bar on the top means we're talking about not B, are mutually exclusive, then the probability of B equals 0.7, and the probability of A union with not B equals 0.6. Find the probability of A. Now, we have been told that this is mutually exclusive, but we have to keep in mind a couple things here. This is not B, but this is the probability of B, and we're looking for A given A union with not B. Well, the first thing we need to figure out is if we're going to use the mutually exclusive formula, which would be the probability of A union not B, and I go with that because that's what we've been given as a union value, that would be the probability of A plus the probability of not B. So we have to, first of all, before we use this formula, we have to find the probability of not B. But we know that if we have an event plus the not of an event, that has to equal 1. So in other words, to find the probability of not B, we're going to subtract the probability of B from 1. And that's going to give us 1 minus 0.7, which is going to give us 0.3. Now coming back over to our original formula, now we have everything we need to figure this out. We have 0.6 right here. We have looking for the probability of A, and we know the probability of not B as 0.3. Subtracting 0.3 from both sides, we know that the probability of A is 0.6 minus 0.3, which is 0.3. So the probability of A is 0.3. Number 5, Jordan rolls 2-sided dice. Determine the probability she will roll a sum that is either even or greater than 5. Well, if we're rolling a 2-sided dice, remember we can kind of set this up as a little table of values. Well, we have 1, 2, 3, and 4. and 1, 2, 3, and 4 as our other die in this little table. If we're looking for the sum, that means we're looking for adding. If we roll 2 ones, the sum would be 2. And we can fill this out, and we'll do it really quickly. If you want to verify it, you can definitely go ahead and do that. But this is going to be like this. With that. So these are the possible outcomes. The first thing it asks us to do is determine the probability that it will roll a sum that is either even or greater than 5. Well, those two events are not mutually exclusive, because we can pick a sum that is even and greater than 5. For instance, if we look at anything to the right of this diagonal line, for instance, anything that's a 6 or an 8 as a sum, they're even and they are greater than 5. So these things are not mutually exclusive. Now, because we want to find the probability that something is even or greater than 5, however you want to say greater than 5, that's okay. We have to figure out what are the number of outcomes that are even or greater than 5 and divide them by the total number of possible outcomes for that rolling 2 die. Well, the total number of outcomes rolling 2 die is 16, because there's 4 possibilities for the first die and 4 possibilities, and 4 by 4 gives us 16. Now we can count the number of events that are even or greater than 5. Well, the even ones, let's just highlight them. It makes it a little easier. We have that one's even. These are the ones that are less than 5. But then we have to figure out the ones that are greater than 5. Well, that's all of these here. These are all greater than 5. Some of them aren't even, but it can be either or. Now going back, we count these up, and that is 14. There are 14 of those events. And if we want to reduce this down, we have 14 over 16. We're going to divide both sides by 2. And that is going to give us 7 over 8. And this one actually can be written as a unrounded decimal because it's terminating. It can be written as 0.875. So the probability of even or greater than 5 is 0.875. Let's look at number 6. Now for number 6, there are 30 students in a class. 16 of these are taking chemistry, and 21 of these are taking biology. Of these students, 12 students are taking both. What is the probability that a randomly selected student in the class are going to be taking chemistry or biology? So in other words, let's see, if we're saying chemistry or biology, that is, what is the probability of C united with B, or if you want to say probability of C or B. Now we can use the probability formula for not mutually exclusive events by saying the probability of C or B equals the probability of C plus the probability of B, or biology, minus the probability of C united with, or C and B, however you want to write that. Let's keep it consistent. Let's go with the and this time. Like that. Well, we know that the probability of C would be the number of students taking chemistry over the total number of students. The total probability of B is the number of students taking biology over the number of students in the class. And then the probability of C and B is probability of both. So that's the number of students who are taking C and B divided by the number in the universal. Putting that all together, we get the number taking chemistry is 16 over 30 plus the number taking bio, which is 21 over 30 minus the number taking both. So we say 12 over 30. Now notice I'm keeping them with the same denominator. It just makes adding fractions easier. I could have calculated the probability separately and reduced them down, but then I'm just having to make that common denominator all over again. So we're going to keep it like this. When we do it this way, just read that here. Normally I like to work vertical, but we're running out of room. So 16 plus 21 minus 12, that's going to give us 25 over 30, which equals reduce down. Let's divide top and bottom by 5, and that's going to give us 5 over 6. So the probability of being taking chemistry or biology is 5/6. And that's using the formula. Well, we could have done this using our Venn diagram. We know that in this Venn diagram, this intersection part right here, that actually has 12 students in it because that's the number taking both. But we don't know how many are only taking biology and how many are only taking chemistry. And we don't know how many are taking neither because there are some out here. But we do know the sum of everything has to be 30. So if I want to determine how many are taking only biology, well, I know that the number taking only B is going to be the total number taking biology, which is, in this case, 21. Subtract those that are taking both. So in that case, 21 minus 12, there's 9. So there's 9 people who are only taking biology. Then for the other part of that, those that are taking only chemistry, I have 16 who are taking chemistry, but 12 of them are also taking bio. So the number taking only chemistry is 4. Now, because if we want to continue filling this out, for those who aren't taking either, well, 4 plus 9 is 13, and 13 and 12 is 25. That means 5/30 minus 25. 5 are taking neither, and that would be outside of B or C or B. So we want to find what is the probability of C and B. Well, from our Venn diagram, the total inside the two circles is equal to the number of C and B divided by, just as always, the total number. Well, that is 4 plus 12 plus 9 all over 30, which in that case, 4 plus 12 plus 9 is still 25 over 30, which is still 5/6. And number 7. In a class of 35 students, 25 are taking mathematics, 8 are taking history, and 5 are taking both. And so that's that class of 35. If a student is chosen at random, what are the odds in favor of not taking either? So we have to be really careful with that word, not taking either. Okay, let's look at number 7. In a class of 35 students, 25 are taking math, 8 are taking history, and 5 are taking both. If a student is chosen at random from this class, what are the odds in favor of not taking either? Now remember, for odds, we need to know the number. In this case, in favor of not taking either, that's actually the number of students who are not in taking M or H. So we're actually looking for the number in the complement of that, because we're going to compare that to the number who are taking M or H. So we are looking for these two numbers. Well, because we've been given how many are taking each subject and how many are taking both, we can actually determine the number of M union H by determining the number of taking M with the number of taking H and subtracting that overlap region of M intersecting with H. Well, the number of taking M is 25. The number of taking H is 8. And the number taking both is 5. So when we put that all together, we say 25 plus 8. That's going to give us 33 minus 5. That brings us back to 28. Now we have that. That's this part right here. But we also need to know those in the complement or who are not taking one or the other. That means we need to determine that, and we can do that by taking the number in the universal and subtracting away the number in the MUH. Now, how many are in the universal? Well, there are 35 in the universal, and there are 28 in the NUH, and that is going to give us 7. So when we're finding the odds in favor of not taking either, it's going to be 7 to 28, but remember we need to reduce these things down. So the odds in favor, dividing both sides by 7, we'll say the odds in favor of not taking either are 1 to 4. Let's keep going. So one card is randomly drawn from a deck of 52 cards, and it's asking us to determine the probability of these two events in each one. So for A, it's what is the probability that the card you draw is a spade or red? So what we're looking for is the probability of spade union red. We can write it like that. So to figure that out, first we can determine, are these two mutually exclusive or not mutually exclusive? Well, if you're a spade, you're a black card, and therefore you cannot be red. So these two events are mutually exclusive. So to determine the probability of their union, exclusive, there we go, we need to find the probability of being a spade and add it to the probability of being red. Well, the probability of being a spade is the number of spades divided by the number in the universal, plus the number here for red is the number of reds over the number in the universal. Well, how many spades are there? There's 13 spades and there's 52 cards in a deck. How many reds? Well, there's 2 suits that are red with 13 cards each, so that's 26 over 52. And we have 13 plus 26, which is 39 over 52. And that can be reduced down by dividing top and bottom by 13. And that's going to give us 3 over 4, or if you will, 0.75. We can write it as a decimal because it's a terminating decimal. Okay, so for B, though, we're asked to find the probability that the card that we pick is a diamond or the card is a face card. Now, these two things are not mutually exclusive because we can have face cards that are also diamonds. So if we are looking for the probability of one or the other, in other words, the probability of diamond or a face card, we need to find what is the probability of being a diamond plus the probability of being a face card. And then we're going to just subtract the probability of them being both diamond and face card. Well, let's look at that as probability. We need to know the number of diamonds to divide by the number in the deck. Oops, I want to add that. So then we want to find the number of face cards divided by the number in the deck. And then the number of cards that are both diamonds and face cards. And again, dividing by the number in the deck. Well, how many cards are diamonds? Well, we know there's 13 and there are 52 in the deck. How many cards are face cards? Well, remember the face cards? Those are king, queen, and the jack. And there are 4 suits, each with a king, queen, and jack. So that's 4 times 3, which is 12 over the 52. And then we have to subtract away the king, jack, and queen that are also diamonds. And so, in other words, there's 3 of those. There's a king of diamonds, queen of diamonds, and jack of diamonds. So we're going to subtract away that. Putting that all together, we get 13 plus 12 is 25. 25 minus 3 is 22 over 52. And then we divide top and bottom by 2 to get 11 over 26. We'll leave it as a fraction. Notice here that I didn't calculate the probabilities individually for either A or B first. It's nice to keep that common denominator so that we don't have to reverse the process at the end. So let's look at part C, a red card or a black queen. Now these two events, these are mutually exclusive, just like in the first one in A, it couldn't be a spade or red. Well, you can't have a red card and a black card at the same time. So these are mutually exclusive. So if we want to find the probability of red or a black queen, we just have to find what is the probability of being a red card and add it to the probability of being the black queen. Well, what is the probability of being red? Well, there are 2 suits that are red. So the number of reds over the number in the universal, we'll get back to that in a minute. And we have to find the number of black queens and divide that by the number in the universal. In other words, the total deck of cards. total number in the deck of the cards. So the number of red cards, like I mentioned, there was 2 suits that are red, so there are 26 cards out of 52. And the number of black queens, well, there's 2 black queens. There are the Queen of Spades and the Queen of Clubs. So we're going to add those 2 together. That's going to give us 26 plus 2 is 28 over 52. And we can divide top and bottom by 4, and that's going to give us 7 over 13. Let's look at the last one here. A club or a 4. Well, there is one card that is a club or a 4, the 4 of clubs. So these, therefore, are not mutually exclusive. So there's that little bit of overlap. So if we want to find the probability of club or a 4, we need to find the probability of the club plus the probability of a 4 and subtract the probability of club and a 4, or in other words, the intersection of those 2. Well, what is the probability of club? Well, we need to know the number of the club over the number in the universal. And I know I'm writing this all out and it seems like it's a lot, but lets the person know who's marking it that you know what you're doing. So let's just always write out our formulas to be very clear. So the number of clubs, well, there are 13 clubs in the deck of 52. There are 4 number 4s, 1 for each suit in the deck of 52. And there is only 1 4 of clubs. That is both a 4 and a club. So there's 1 in the deck of 52. And that gives us 16 over 52. And we can reduce that down a little bit by dividing top and bottom by 4. And that's going to give us 4 over 13. Okay, let's look on to the next question here. It's saying a survey of students was used to estimate the percentage of students who do homework in the evenings and the percentage who watch TV. The survey found that 52% did homework, 45% did homework and watched TV, and 75% did homework or watched TV. So let's be careful of the and the or, because we know that 52% did their homework. We can convert that to a probability of homework. Let's do that right away before we even go into the question. The probability of homework is move the decimal 2 places to the left is 0.52. The probability of homework and TV, well, that is the intersection. So we'll say homework and TV. Converting that to a decimal is 0.45. And the probability of or TV, we'll convert that to 0.75. So we have these probabilities here. We want to know what is the probability that a randomly selected student watches TV only. So what is the probability of TV only? That would be, we need to know how many students fall in this only TV area here. So we need to kind of figure that out. Well, to figure that out, we could go back to our not mutually exclusive formula. We can start by saying the probability of H or TV equals the probability of H plus the probability of TV minus the probability of H. So we can use that to find the probability of the TV? Well, let's fill in what we know. We know that OR is 0.75. Probability of H is 0.52. We're looking for this. And we're going to subtract the 0.45. Now, we can combine this with this first to get 0.75 equals 0.52 minus 0.45 is 0.07. Probability of TV. So I'm going to subtract 0.07 from both sides. Let me just bring that up here. So that means the probability of the TV, that's going to give us 0.75 minus 0.07, 0.68. There we go. But that includes the whole thing. That includes everything here. We only want to find the only region. So we are going to subtract away one of these. We're going to subtract one of the intersections away. So the probability of TV only is going to equal the probability of the TV minus the probability of that intersection. And that's going to give us 0.68 minus 0.45, which is going to give us 0.23. And there we go. All right, let's look at number 10. In a certain model of cars, 43% have heated seats, 36% have a sunroof, and 49% have neither. Determine the probability of a car having both heated seats and a sunroof. Well, to have both heated seats and a sunroof, you're going to be looking at, we want to find what is the probability of heated seats and sunroof. That means we're looking for this region right here, this probability of that region happening right there. So that means, let's see what we know. Well, we know the probability of heated seats. The probability of heated seats is 0.43 as a decimal. Remember, probability must be in a decimal. The probability of a sunroof, well, that's 0.36. And the probability of neither, well, that's actually all that region outside of here. Okay, so outside of the union of these two things. So we're actually looking for this kind of all this outside of here. I know we're kind of going over the lines a little bit there. Everything outside of the union is what we're talking about when we talk about neither. So if that is neither, that we can write that as what is the probability that it is not HS or sunroof. It's like being in the complement region. And we know that that is 0.49. So we need to figure out what is the intersection of those. And in order to do that, let's go back to our formula. So the probability of HS or SR equals the probability of HS plus the probability of SR, in other words, sunroof, minus the probability of both HS and SR. Well, we know this. If we knew this, we could figure it out. Well, we don't know it directly. We actually have to calculate it. But we can calculate it from this part because we know that the probability of everything has to be of not equaling, of not equaling HS or SR. Let's write this down. So the probability of HS and SR, HS or SR, plus the probability of not HS or SR, all of that together, that's got to equal 1. In other words, the probability of HS or SR has to equal 1 minus when it's not. And we know when it's not. It's 0.49% of the time, 49% of the time, or change to a decimal point 49. So we get 0.51. So now that we have that, we can go back over here, fill it in, simplify, and isolate. So we have HS is 0.43, SR, sunroof 0.36, minus that, both, and keep going, 0.43 and 0.36, that gives us 0.79. Let's subtract 0.79 from both sides. And that's going to give us 0.28. Sorry, it's going to give us negative 0.28. Let's be careful with our negatives. Because remember, on this side, we still have negative P HS union SR. Remember, when that happens, we can make them both positive so that the probability of having both the heated seat and a sunroof write it in words equals 0.28. All right. Now it's saying, what are the odds against heated seats? Well, let's assume that this was out of 100. So the odds against heated seats, if we assume that the total thing was 100, and that would make that these things being out of 100, which would just give them 43% of 100 is 43 and so forth. So we said that the odds against, well, we would have to find what is the number against heated seats. Well, what is the number for heated seats? And then we would have to find the number, because it's against, the number for not heated seats. Because remember, against has to go first. So let's figure that out. The number for heated seats, that is 43. That means the number for, what as we call it, not heated seats, assuming that it's 100, that would have to be 100 minus 43. So now we get 57. So putting this back into our ratio, that would be 57, because that has to be first, because it's the against, not heated seats. Against heated seats. So 57 to 43. And the last one. Now this one here, we're given our set in set notation. We're given that union equals, remember in set notation, this can be translated as, let me give a pointer here, x such that, that's what the line means, x is less than or equal to 10, where x is an element of the natural numbers. And remember, the natural numbers do not include 0. There is no 0 in the natural numbers. The first set inside this universal is x such that 2 times x, where x is an element, or x is less than or equal to 5, where x is an element is still of the natural numbers. Well, we can actually write out this set. All we're going to do is replace this x here with numbers 1 through 5. So when this x equals 1, the first number in the set is 2 times 1, which is 2. When the next number is 2, 2 times 2 is 4. The next number in our set is x, which is 3. Plugging it in, 2 times 3 is 6, and so forth and so on. We can do it that way, and that gives us these 5 numbers. If you like, you could set up a little table of values like that, where we put our 1 through 3, 4, and 5, that's those 5 natural numbers, and we substitute them in for the x. So we get the same idea, but just kind of really, showing all the work. Just like that. It was 5. Getting ahead of myself, which is 10. Now the other one, the set B inside this universal, are those numbers that are multiples of 4. Well, the universal is those natural numbers 1 through 10, which is just 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And there's only 2 numbers that are multiples of 4, and that is 4 and 8. So part A says determine the probability of drawing the number of elements in set A and set B. Okay, well, let's put the numbers in our Venn diagram over here. Well, number 1 in the universal set, that is not in either. So we're going to put it there. Number 2, however, that's only in set A. So we're going to put 2 here. 3 is in neither A or B. So we put it there. 4, however, is in both. So we're going to put it in the intersection. And we're going to continue to do this for the rest of our numbers. So notice here, the even numbers are inside A or B, and all of those odd numbers are on the outside. They are in the complement region. So we're asked to find what is the probability of set A and set B. So really what we're being asked to find is what is the probability of A intersect with B. So we're finding this region here. Well, first of all, we have to find how many numbers are in that region there, divided by the total number in the universal. Well, how many numbers are in there? Well, there are 4 and 8, which is 2. And the total number in the universal is 10. Well, dividing everything by 2, we get 1 over 5, or we get 0.2. Okay, let's look at B. Determine the odds of elements neither A nor set B. Okay, so they're not A or B. If they're not A or B, let's make this the odds in favor of elements neither A nor B. All right, so that means A or B, the number, of neither A or B would be the complement of the union, where the number for the union. So we have to look at both of these. Well, how many are in the union? Well, the ones that are in the union, there are 5. It's all the even numbers, 2, 4, 6, 8, and 10. So there's 5 here. How many are not in the union? Well, those are all the odd numbers. So it's 5 to 5, but we always reduce our odds. So the odds in favor of neither A or B is still 1 to 1. Well, that's the end of this lesson. Remember, if you have any questions, to get in touch with your teacher. I hope you have a great rest of your day. Take care.